Good morning, everyone. I'd like to convene the third day and the first session of this morning. We have kind of a panoply of subjects that we're loosely putting together under the rubric of keeping an eye on things, whether that's keeping an eye on your machines or keeping an eye on the sky or keeping an eye on bad people coming out to get you, just keeping an eye on things. Our first speaker is from the Noir Lab in Tucson, Arizona, where it is substantially drier than here, but maybe no less warm. So let's give a warm welcome to Yuanyuan Zhang from the Noir Lab, who will talk to us more about astronomy that's not Rubin.
Yes. Oh, thank you very much. Especially thank you for putting me as the first talk on Thursday. I got really nervous. Let me just start with talking a little bit about how I have been using OSPool for a small cosmology analysis that I worked on with some collaborators and students. So a little bit of introduction first. What we did for this analysis was so-called galaxy cluster cosmology. I will start with telling you a little bit about what is galaxy clusters. If you can see this beautiful image from Rubin, I don't know if it's possible to darken the lighting in the room a little bit. Okay, cool, thank you. So now this image finally looks beautiful. This is from the Vera Rubin Observatory. There are many, many galaxies inside of this Vera Rubin Observatory and astounded the world last year when it was released. When you look at images like this, sometimes you can see spots in the sky with a lot of galaxies tightly packed together, like what is shown in the bottom here. So this structure has a lot of those very yellowish round galaxies inside of them, and they are gravitationally bound together. When you see some spot like this, congratulations, you have found a galaxy cluster. They are really known as clusters of galaxies because astronomers are really bad at naming things. But I usually call them galaxy clusters, so it sounds a little bit shorter. If you look at the image very carefully, you can actually find a bunch of galaxy clusters inside of them. For example, there is one galaxy cluster that's a little bit smaller to the bottom one here in the middle of this image. And if you also look to the side of this image, you can find a galaxy cluster that looks a little bit redder and a little bit smaller. And this galaxy cluster looks a bit smaller because they are significantly further away than the other galaxy clusters, than the other two galaxy clusters in this image. And if you are used to finding these very small, further away galaxy clusters, if you look more carefully, you can even see more of them in this image. For example, a little bit here, and then a little bit here. So galaxy clusters, you can find a lot of them, especially if you have a good image from the Vera Rubin Observatory. Now, theoretically, galaxy clusters are very interesting objects as well. They are known as the most massive gravitationally bound structures in the universe. So you're not going to find something that's gravitationally bound that's more massive than galaxy clusters. And when you look at these dark matter simulations, these simulations of matter distributions in the universe produced by theorists, galaxy clusters usually correspond to the densest points in these matter distributions. So for example, in this bottom one here, galaxy cluster correspond to this little nexus point of all of the matter distribution there. And in this one, there's a lot more nexus points of all of the matter distributions. These densest points in this matter distribution usually observationally correspond to a galaxy cluster. And one interesting thing about galaxy cluster is that depending on your cosmological parameters, how fast your universe is expanding in theory, and how much matters you have in your simulations, the galaxy cluster sizes and their densities vary a lot. For example, in these two panels here, the average matter density in the universe is quite different. And in the bottom figure there, you can see that the galaxy cluster sizes are much bigger and they're also much rarer, which means that observationally, galaxy clusters are known to be cosmological probes, probes of the cosmological parameters, especially the important parameters like the universe average matter density omega m and the fluctuation amplitude sigma 8 and other parameters there. So when we do cosmology with galaxy cluster observations, nowadays the buzzword is machine learning. So you can certainly use machine learning to do galaxy cluster cosmology as well. And the method that got really popular in the past couple of years is known as simulation-based inference, or SBI. In this kind of SBI approach, you would first decide on what kind of observables you wanted to study for your cosmology. For example, some observables related to galaxy clusters. Then you generate a bunch of simulations of these observables from your cosmological parameters, vary your cosmological parameter values. And then you use a machine learning algorithm to map out the relations, the probability distributions between your parameter values and your observables that you would see. And after fully training the machine learning model, then you can use it to derive the posterior parameter based on whatever you see in your telescopes. This kind of machine learning-based algorithm has a lot of advantages compared to the more traditional method, especially the Markov chain Monte Carlo method, MCMC. So here is some of my very unscientific diagrams illustrating the differences between the more traditional MCMC method versus the SBI method. For the MCMC method, you first determine a value range for all of your cosmological parameters. This is called the prior range in Bayesian statistics. And then from these prior ranges, you sample some possible values of your parameters, and then you generate what your observables would look like according to your specific models. Then you bring your observations, calculate some quantities called likelihood, and according to the likelihood value, decide whether or not your initial sampling draw is good or not. You either reject or accept your initial samples of the values, and then repeat the process many, many times until you got a posterior constraints of your parameters that you are interested in. For this MCMC process, every step that I have just described is interdependent. And if you use many processors to do the process, each of the processors needs to know what the other processors are doing. So if we want to have a fast Markov chain Monte Carlo analysis, we always have to run it on a high performance computer. And even worse, the MCMC process actually doesn't scale that well. So for me, myself, I have been able to use the MC process effectively with about 250 processors. And some of my more skilled colleagues have been able to use 500 parallel processors for the MCMC process. And beyond that, it doesn't save you any time anymore. So as cosmologists, we are used to just sitting for a month in front of the computer, waiting for our HPCs to deliver our chains, because we cannot effectively use all of the nodes, and everything just has to go slowly while the HPC does the work. Now, then you bring in the SBI-based method. So the SBI method actually shares many components with the MCMC method. You still need to decide on a prior range of all of the cosmological parameters. And from the prior ranges, you sample what your universe observables would look like. You generate many model predictions, which we call simulations there. And then you bring in a machine learning algorithm. You layer the mapping relations between the simulations and your parameters. And after this step is done, you can finally bring in your observables and derive your posterior constraints on your cosmological parameters. The good thing about this process is that the most computationally intensive part, which is to calculate all of those simulations, they're all independent from each other. Each of the simulations does not need to know what the other simulations are, because you are generating many, many more of them. This means that it's very well suited for a high throughput computing process. And you can do this process much easier, and it practically has no scaling relation, especially when it comes to generate the simulations. So the high throughput computing is
feeling for how much data and how much memory you need for each of these simulations.
Yeah.
I don't know if it's coming next, so I will wait.
Yeah.
But it will be useful for us to understand, because if you are bringing us a new, a new paradigm for using HTC, is to understand what are the requirements of each of these independent task. Okay, so
Yes.
thank you.
So this actually depends on what kind of simulations you make. But for for this pilot study that we're using for galaxy clusters here, we started with keeping things very simple. And we decided that we would keep a 16-element data vector as our observables, which means that the models to generate this is purely analytical and does not use a lot of memories and does not use a lot of processing power. And each of the simulation can be generated very quickly within about a minute. And for the training and testing samples, we just ran it on the OSPool. And this was especially helpful because at that time, none of my collaborators had access to any computing clusters. We only had our laptops. So using OSPool, we were able to use about just like thousands of CPU hours, and we ended up with 500,000 training and testing samples for this SBI purpose. And I still remember when my collaborator asked me, how long do I intend to run it on my laptop? I said, I already have the training and testing samples thanks to OSPool. And that was like 2 hours later. And because this analysis is fairly simple, it's a pilot study, we kept everything very simple. After generating all of the training and testing samples, especially in terms of these 16-element data vectors, I was able to do the training of the machine learning algorithm and all of the further analysis on my laptop. Now, if I were going to go back and do this again, the models would get more complicated, and I would also know to actually train the machine learning model on OSPool because GPUs does make the training process much faster. It's a difference between seconds versus a couple of hours on my laptop. So we built up the SBI method and using OSPool, and we also compared the analysis to a more traditional Markov chain Monte Carlo based analysis. We are very happy to report back that the two methods are actually very comparable in terms of parameters. We tested the method for a bunch of different ranges, including in-domain applications, out-of-domain applications. For the parameters we really care about, especially omega m and sigma 8 in the red boxes there, you can see that the SBI method and MCMC gives us very good comparisons for these two parameters. There are some other parameters that they don't compare that well. We don't worry about them. We understand why they were different, and I actually really liked the SBI-based constraints there. Because we have so many training and testing samples, we were able to really test out this SBI method. So I'm not going to talk about the whole range of the tests that we have done around this machine learning-based method, but just want to talk about one thing that enabled us to do about SBI, which is how these parameter constraints changed according to the number of training samples we use for the algorithms there. So the little panels here shows the performance around each of the parameters compared to the x-axis, which is the number of training simulations we used for the algorithm, for the machine learning algorithm. And for the parameters we really care about, omega m and sigma 8, the parameters usually reaches pretty good performance around about a size of 2,000 training samples. This is where usually people stop for the simulation-based inference. But if you increase the the size of your training samples here, that you can see that you start getting, you start getting additional information on other parameters like this Ln sigma and B here. You seem to only start gaining constraining power on these parameters after you have pinned down the other parameters. So this was interesting to see that actually getting a bigger training sample help us constrain the other parameters, the astrophysical parameters, in addition to the cosmological parameters. So I'm not going to talk in many details about all of the other statistical analysis. And before I move on, so I wanted to say a big thank you for OSPool. This really enabled us to do this small pilot study. And I think it's very well suited for a high throughput computing resources here. Okay. And now I can move on to the next topic. So we're going to go away a little bit from machine learning and OSPool for now. Yeah, thank you. I hope you enjoyed this little machine learning-based analysis, but that was not enough to convince NORALab to send me here to medicine. And the real reason that I convinced them to let me come here is that I promised them I would learn how to put users and data close to compute. So I am based at the National Optical Infrared, National Optical and Infrared Astronomy Research Laboratory, NORALab. We are the institution that manages a lot of the telescopes for the National Science Foundation. And the most famous one is the Vera Rubin Observatory, which you have heard a lot about this week. But we also operate many other telescopes, especially the Gemini North and South telescopes, the Blanco telescope, and the Mayo telescope. They are known as the workhorse telescopes in optical astronomy, and they produce a lot of data as well. These telescopes produces about petabytes of data at NORALab, which are served to users and the whole astronomy community. Mostly they are available through the Astro Data Lab and the Astro Data Archive, two services. But I would say most of the users would only access them through the Astro Data Lab. So let me talk a little bit more about the Astro Data Lab here. The PI of the Astro Data Lab, the PI of the Astro Data Lab is Robert Nikuta. So he is the one that's guilty for all of those developments of the progresses here. And I would have to bring back all of the questions back to him. Just to be clear, Robert is the one on the left side of this very cute photo here, not the one on the right side. We still like Robert, nevertheless. The little one there is actually Robert's baby. So the Astro Data Lab serves data over about 30 major astronomical surveys. We initially started with serving data from NORALab telescopes, but now it has included data from other facilities as well, including data from European observatories and NASA telescopes, and also some of those gigantic simulations that was made for LSST as well. NORALab, the Astro Data Lab now has over 5,000 registered users. So this plot here, this figure here shows the amount of users we have over the years. The blue spikes in this figure is the amount of new daily registered users. So on a daily basis, we get about somewhere between 5 to 10 users. And the yellow curve there is the accumulated amount of total registered users. So the Astro Data Lab's user base has been steadily increasing in the initial first a couple of years. And in the past couple of years, that has actually started increasing exponentially. This is very exciting, but also a little bit scary at the same time. So we need to think about how to serve the users better. Most of the users have several ways to access and use data through Astro Data Lab. Most of the users access and analyze the data through a local Jupyter server that was set up on a local computer server at NORALab, but they can also access the data through web interfaces and command line interface. On a daily basis, the Astro Data Lab gets about tens of thousands and sometimes hundreds of thousands data queries from the users. And in a single year, that amounts to tens of millions of data queries. So this map here shows the amount of data queries coming from all over the world in 2024. So far, we've been able to cover almost all of the continents except Antarctica. So we're still waiting for that single user coming from Antarctica. But most of the users actually are based at the United States, which accounts for 82% of the use cases at Astro Data Lab. So I hope all of these achievements, all now achievements by Robert Nikuta impresses you. What is most inspirational to me is that all of those services are actually produced or served from a very modest compute server based at the NOAA lab. We don't really have any compute to the users other than that little Jupyter hub that people spun up to access and play with the data. So we are really interested to hear how to put the users and this data close to HPC and HTC style compute. And I've talked to many of you already this week. Thank you for coming to talk to me about OSDF and Pelican. But if you have more suggestions and comments, I would really love to hear about them. So please come to talk to me. Thank you.
Thank you. Do you have any questions?
All right.
Yeah, Christina.
Yes. So this is about the OSPool part of your talk. Sorry, even that's not the real reason you're here. So when you were using the OSPool, did you have students use it? And in your use and/or your students' use, is there something we could do better to make it more useful, easier to use? Examples we could give? Any improvements?
Right, so I am the only one that was using it. I tried to have a undergrad actually sign up for OSPool very recently, but I think she got a little bit scared of the process there. I think I'm not really sure the process, was expecting like undergrads to sign up for their account. So maybe we can talk a little bit more about this afterwards.
Also on the OSPool, so you described your project as a pilot, and that it took a few minutes for each task to run. So what's the next version look like? What does it look like to move that forward?
Yes, so to keep everything simple, we ignored all of the observational effects, selection effects, and the systematic effects. Only from very theoretical models. To make things more complicated, we need to add in all of these observational effects, but that would make the models much more complicated, and I think would increase the computing time from a couple of minutes to maybe 10 times longer. Yeah.
A question about the second part. You're saying a query. What is a typical query? Is it fetching an object from, or how do you see the query connecting to the compute?
Yes, so a query is basically a user, that do some searching on a single catalog or table that they said, I want the data around this area of the sky. And with a Jupyter Hub, with their usage of Jupyter Hub, which is where 60% of the users are, they usually use the data and then they make some more analysis on top of it and then make some plots of it.
So they come and say, I want this section of the sky at this time or something like this. This is a query. And then you deliver to them a bunch of files, and then they use the Jupyter notebook to manipulate these things.
Yeah, exactly.
Okay. And all this at the moment is happening on your resources.
Yes.
You create the copy locally, and they run the Jupyter notebook locally, and you envision a similar queries, but where the computing can happen in other places.
Yes. So
that's where you would like to be.
Yeah. So 60% of the users are using the Jupyter analysis now, but actually we are missing out on some of these users that we do have these examples. They actually download the data, they query the data, they download it somewhere, and then they upload it to their own HPCs or HTCs. So this is the part that we actually want to solve.
Yeah, you have to create a copy of the data close to the compute. I understand it. Now, one thing that would be useful, I think, while you are here is for us to understand what is your query interface, because whatever we are going to do will need us to be able to use your indexing, because we have, the user says, I want this. Then we have to come to you and to get the object. And then we can do our, but we should move on. Okay, but I want to make sure that while you are here, we have a discussion about how we talk to your indexing service.
Okay, thank you.
Thank you. Let's give a round of applause for our speaker.